Hello friends. In the last class we were discussing partial molar properties. We defined the partial molar properties as the partial derivative of any extensive property with reference to the number of moles of a particular species. So if the partial molar property, if volume is, let's say, V, capital V, then the partial molar volume of species I is defined as del V by del Ni when the other properties, including the number of moles of all the other species, is kept constant. Particularly the other properties, we are talking about temperature and pressure. So when pressure, temperature and the number of species of all the other species are kept constant, the rate of change of the volume with reference to the number of moles of species I is called the partial molar volume of species I. This is what we had derived, and then we said that the change in volume due to mixing is actually calculated by the difference between the partial molar volume of species I and the molar specific volume of species I pure substance, okay, at the same temperature and pressure. Okay. In the same fashion, we said the changes in each property, extensive property, such as internal energy, enthalpy, entropy, can be evaluated by calculating the difference between the partial molar internal energy or partial molar enthalpy, partial molar entropy at a given temperature and the partial pressure, and the same quantity of a pure substance at the same conditions of temperature and pressure. Okay, so this is basically what we had found in the last class, the changes in properties due to mixing. And going further from there, we said that since the internal energy of a substance is constituted by properties temperature and pressure as well as the composition, so the U would then be a function of Tp as well as various other functions. And we started with the generic equation for a compressible substance, where we said du is equal to Tds minus Pdv. So U is a function of S and V, with T being a partial derivative of U with respect to S and P being a partial derivative of S, the U with respect to V with a negative sign. This is something that we had seen for a pure substance. Here we added the other variables, which is N1, N2, N3, which is the number of moles of individual constituents. Right. So that is, let's go to the whiteboard and take a look at that slide. So we had said that the internal energy of a pure substance is a function only of S and V because of this, and T is written as del U by del S at constant V, and P is written as minus del U by del V at constant S. But in the case of a mixture, we will have also N1, N2, N3 up to Nn, and therefore du, if I mathematically differentiate it, will get a del U by del S at constant V and N, and into ds, plus del U by del V at constant S and N into dV, plus for each species, so you will get del U by del N1 dN1 with S and V as well as all other N's, N2 to Nn kept constant, plus del U by del N2 dN2 with N1, N3, etc. up to Nn kept constant along with S and V and so on. So you get a summation like this of del U by del Ni into dNi, where S, V and N j not equal to I are kept constant. Now you define this quantity del U by del N1 as mu1, del U by del N2 as mu2 and so on, then all these are kept constant. So you define them as what is called the chemical potential. So this chemical potential, therefore, in this equation, if I look at it, it looks like additional mechanisms of work transfer. So this is this stands for the heat transfer, this stands for the compression work, and these stand for the chemical work that is done due to the changes in number of moles of each species I. Okay, so that is the way we interpret this, because the du, which according to first law, is caused by the heat transfer or work transfer due to various modes of work in this system with multi-components like N1 to N. There are N additional modes of work because of change of each of these species. So if I take each one of these as a generalized coordinate for each mode of interaction, then the corresponding generalized force works out to be mu I according to this equation. So mu I is the generalized force for chemical work, and the Ni is the generalized coordinate. So mu I dNi constitutes the mode of chemical work that is done to change the number of species, to change the number of moles of a species I by dNi. Right? So that is the concept that we learn. So you learn an additional concept where there is chemical work, and the chemical work is basically given as the product of the generalized force, which is the chemical potential of the species I, and the change in the generalized coordinate, that is dNi. Right? So this is basically what we understand in this statement. Now going further, we also did the other forms of energy that we have defined in thermodynamics. H is defined as U plus PV for a compressible system. Now this U plus PV, if I differentiate, I get dH is equal to du plus PdV plus VdP, and if I substitute for du plus PdV from this equation, so du plus PdV becomes TdS plus summation of mu I dNi, then I get it's actually VdP plus TdS plus mu I dNi, right? So this is basically what you get. So you substitute for du plus PdV as TdS plus summation of mu I dNi, you get this. So dH is also written in the form of VdP plus TdS plus this. In the same way, we write dG is equal to VdP minus SdT plus summation of mu I dNi. Okay, and dA, which is the change in the Helmholtz function, as minus PdV minus SdT plus summation of mu I dNi. So from each of these, if I write in the form of Maxwellian relations, so then I'll get the mu I. From the first equation, we got it as del U by del Ni when S and V are kept constant, or the species are kept constant. From the second equation, that is this one, we get it's a function of P and S. Okay, so del H by del Ni when S, P, and Nj not equal to I are kept constant. That is again same mu I. The same mu I here actually becomes when pressure, temperature, and all other species are kept constant, del G by del Ni, and temperature, volume, and all other species are kept constant when dA by del Ni. Now in this, we have defined when pressure and temperature are kept constant and all other species are kept constant, the partial derivative of a particular variable with respect to Ni is the partial molar function of property. So according to these definitions, the potential, chemical potential, actually becomes the partial molar Gibbs function of a species as it exists in a solution. Right? So that is basically what we understand. So chemical potential of species I as it exists in a mixture at a constant temperature, pressure, and N, I is equal to 1 to N, that is defined as the partial molar Gibbs function of the species I as it exists in the function, exists in the mixture. Right? So that's the thing that we understand. Now, going a little further from what we had done in the last class, if I say mu I is equal to del G by del Ni when temperature, pressure, and Nj not equal to I are held constant, okay, and therefore it is the partial molar Gibbs function Gi. Okay, now let us try to do some mathematical manipulations to come come up with a very useful relationship called the Gibbs Duhem Equation. So now G, the Gibbs function of the mixture, will be the summation of Ni Gi bar. This is the way we define partial molar properties for all mixtures. So from I is equal to 1 to n. Because we had defined that any generic extensive property X is the summation over I is equal to 1 to n of Xi so okay, this is X by n. Is defined as Xi bar, or this is X is also equal to summation of I is equal to 1 to n of Ni Xi bar. This is the way we had defined the partial molar properties. So if for X I substitute G, I get this one. So the Gibbs function of the mixture, the extensive property, is equal to summation of Ni Gi bar, is something which we can say. Okay, or this is also equal to summation I is equal to 1 to n of Ni Ui. Okay, where Ui is the partial molar Gibbs function or mechanical potential. So I can write this. So from this, if I just differentiate this, I get dg, which will be, if I can differentiate this, it will be the summation from I is equal to 1 to n of, for each species, I will get a Ni d mu I plus mu I dni. Okay, so it's basically differentiating this by parts, so we will get Ni d mu I plus mu I dni. This is basic differential calculus. Okay, so now this is your first expression that we get through here. But at the same time, we also know that dg is v dp minus s dt plus summation of a is equal to 1 to n of mu I dni. Okay, we got this from the previous page where we defined all this. So dg is v dp minus s dt plus summation of mu I dni, where we derived it from the basic thermodynamic relationship. So if I compare these two expressions, I'll see that the summation of mu I dni is common to both of them. So if I just remove that, then I'll be able to say this is equal to this. So the mu I dni summation gets cancelled. I get Ni d mu I. So I get summation of n is equal to 1 to n of I is equal to 1 to n. I is equal to 1 to n of Ni d mu I. Okay, the mu I dni gets cancelled on both sides, is equal to v dp v dt minus s dt, or I can take everything to one side and write v dp minus s dt minus summation of Ni d mu I equal to 0. Now this relationship or this equation is called the Gibbs Duhem equation. This is a very useful equation which will be useful to find compositions of mixtures by equating v dp minus s dt to summation of Ni d mu I, and knowing the values of chemical potentials Ni's can be calculated, or knowing the value of Ni mu I can be calculated. So this is a very useful relationship that is often used. Okay, we can actually go a little bit more general. Right now we just did it for the Gibbs function, but if I write it for any general extensive property X, then the same equation looks like X is equal to summation of I is equal to 1 to n of ni xi bar. Okay, this is also equal to n times x bar of a mixture. Okay, where n is the total number of moles, which is summation of ni. Okay, total number of moles of the mixture multiplied by x bar, which is the specific x of the mixture, x by n of the mixture. Now, if I differentiate both of these independently, so the first thing I do is write dx is equal to, by differentiating this one, then I'll get del by del t, because x is a function of temperature, pressure, n1 and n. Okay, so when I differentiate with respect to each of them. So I'll write this del x by del t into dt plus del x by del p into dp, where what is kept constant can be written here. P is kept constant and n I equal to 1 to n is kept constant. Here t is kept constant and n I is equal to 1 to n is kept constant, plus I'll get a summation from I is equal to 1 to n of del x by del ni into dni, when t, p and n j not equal to I are kept constant. Now this we can write as, this is the xi bar, which is the partial molar x, because it is del x by del ni when Tp and Ng not equal to are kept constant. So this can be written in the form this can be written in the form del x by del t dt, del x by del p dp, plus summation of del x by del ni dni. Okay. At the same time, we can also differentiate this one. This is also equal to nothing but summation over I is equal to 1 to n of ni dxi bar plus xi bar dni. Right? So this is also a thing that you get. So this xi bar dni would get cancelled on both sides. So I'll be able to write summation from I is equal to 1 to n of ni dxi bar is equal to this, the rest of it, del x by del t dt at constant p n plus del x by del p at constant t n dp. Right? This is the expression that you get. So this is the more general form of the Gibbs Duhem equation. So here for x, if I substitute g, I get this expression. So ni dgi plus del x will be del g by del t at constant p, and del g by del p at constant t will, from Maxwell relations, constitute the v and minus s that you get here. So you get this Gibbs Duhem equation when I substitute x is equal to g. But if I also substitute x is equal to u, x is equal to v, and x is equal to h, x is equal to a, I get different forms or different versions of the Gibbs Duhem equation. Okay, so this is a general form of the Gibbs Duhem equation that we can use. Okay, so this is something that we need to keep in mind, and Gibbs Duhem equation is useful. We'll talk about it when we go to the next module on phase equilibrium and chemical equilibrium. But right now, let's keep this as a result which will be useful in future. Okay, at the moment we'll not bother. The next thing that I wanted to talk to you in today's class is how do you evaluate partial molar properties? Okay, so we have defined partial molar properties, but how do you evaluate them? So it's actually not a simple, straightforward thing to evaluate partial molar properties, because suppose I have a mixture of n constituents. Okay, let's say I have let's say liquid mixture of all miscible liquids. Let's say water, ethanol, methanol, some aldehydes, ketones, some things of that kind. Let's say they are all mixed together in the form of mixture. Now, how do we evaluate the partial molar enthalpy, partial molar specific internal energy, partial molar various properties? So the only property that is easily measurable is the volume. So it's easier to visualize measurement of partial molar volume. But by calorimetry and other methods, we can also quantify the changes in energy that happen because of mixing, and from that we'll be able to evaluate the other properties. So now let us just talk about volume. That's easy to visualize. So suppose we want to measure partial molar volume. Okay, so suppose I want to measure VI bar, then we recognize that VI bar is equal to del V by del Ni when temperature, pressure and N J naught equal to I are kept constant. Then we basically measure the volume, capital V, by changing the number of moles. You keep a mixture. I know the number of moles of each of the constituents that I have mixed in that mixture. Okay, so I know the composition of the mixture. So I know its volume. Now I add dni moles of species I, keeping the temperature the same, the pressure the same, and all the other species the same. And now I measure the volume again. So if I can measure the change in volume because of the change in this one, so I can actually measure delta V, and I can for a given delta Ni. So then I can say that with T, P and N J naught equal to I kept constant. So what have I done? I have taken a mixture with a known number of N1, N2, N3, N4, Nn, and then only species I take delta Ni moles of species I and add it to that mixture, and I also measure the volume again and find out what the change in volume is. And the change in volume for the change in delta Ni, when all the others are kept constant, becomes this. And so delta V by delta Ni, when delta Ni tends to 0, the limit, this constitutes the value of VI bar at that composition. Okay. Now, if I want to know the VI bar at all compositions, then I will need to make this kind of a painstaking measurement by varying N1, N2, N3, etc., Nn in a very, very gradual manner by adding one species at a time and finding out the change in V and recording it and calculating the partial molar properties. So you can actually calculate the partial molar properties for various values of N1, N2, N3, Nn by gradually varying each of these individual quantities. So this is one method of measuring, and now that we know that volume can be easily measured, this can be visualized. In the same fashion, if I have the method, we have methods using calorimetry to deduce the values of, let's say, the internal energy, okay, and from that we can calculate the other properties. The internal energy can also be measured in the same fashion by measuring the value of U at given temperature, pressure, and N, I is equal to 1 to N. Suppose I know the value of U by some calorimetric method. Okay. Now I add delta Ni moles of species I while keeping the temperature, pressure, and all the other moles numbers constant, and I measure the value of U. So I get the change in U between the initial state and after adding Ni. So I know the value of delta U and I know the value of delta Ni, right? So I can actually plot delta U and for various values of Ni like that, and the slope at each location will be this. So limit as delta Ni tends to 0 of this will give me Ui bar. Okay. So likewise, if I measure Vi bar and maybe Ui bar, then from that I will be able to evaluate the other quantities by using the relationships that I have between the various things. So measurable properties usually are volume, pressure, and temperature, and indirectly through calorimetry one can probably determine the value of internal energy, and then we'll be able to use those for evaluating the various other quantities. So this is basically the method of measuring the partial molar properties. We can demonstrate by showing how to measure partial molar properties for a binary mixture, that is a two-component mixture. Okay. So we use what is called the method of intercepts for a binary mixture. Of, let us say, A and B are the two substances. Okay. So what I try to do is to measure, suppose this is Xi, this is the mole fraction of Xa, let us say, Xb. Okay. So I can draw two lines here. One is Xb equal to 0, and here Xb equal to 1. And since it's a binary mixture, here you will have Xa equal to 1 and here Xa equal to 0. Okay. So Xa equal to 0. Okay. So suppose I measure the volume per mole V by N, and I measure it at different locations, and I get a curve that goes like that. Okay. So this is the specific volume of pure B, because here the here Xb is 0, so it's pure A. Okay. The Xb is 0, so it's pure A. So the specific volume that you measure is that of pure A, and similarly at this end, since Xa is 0, this is specific volume of pure B. So at anywhere in between, if I want to get the property, which is the partial molar property, then I can use what is called the method of intercepts. How do I do that? So if I recall the expression, so suppose here I write X is equal to Na Xa bar plus Nb Xb bar, because it's a binary mixture, only two substances, so Na and Nb are the two, and so if I divide this by N, I divide this by N, divided this by N, where N is equal to Na plus Nb. So I get, this is Xa, mole fraction of A, and this is Xb, the mole fraction of B. So I can write X bar, this is the mole fraction of the mixture, sorry, the specific volume of the mixture, and this X bar is equal to um, xa bar plus xb bar. Okay. In this particular case, we were talking about volume, so I can say V bar of the mixture is equal to XA VA bar plus XB VB bar. Okay. So then, if I write the derivative, we can actually draw parallels for that. Let me do it with the more generic variable. So if I write dx bar by dxb, okay, so I differentiate this with respect to xb, then since this xa is 1 minus xb, okay, which is the mole fraction, because since Na plus Nb, so if I divide it by n, I get 1, which is equal to xa plus xb. Okay, so xa plus xb is 1, and therefore I can write xa is equal to 1 minus xb. So if I do that, if I differentiate with respect to this, then I'll get terms which look like 1 minus xb into del xa by del xb plus the second term xa bar into minus 1, that's right, plus similarly in this one I'll get xb into del xb by del xa and del xb plus xb bar. Okay, so this is the expression that we will get, and now you can make use of the Gibbs Duhem equation that we just derived a few minutes ago. So the Gibbs Duhem equation for this binary mixture can be written as, just a moment, I'll find the page. Yes. So we had said that at constant pressure and temperature, so your Gibbs Duhem equation that we derived for the most generic case was this one. So when pressure and temperature are kept constant, Ni dxi summation will be 0. So at constant Tp, I get summation from I is equal to 1 to n of Ni dxi bar is equal to 0. And if I write this for a binary mixture, it will be Na dxa plus Nb dxb equal to 0. So that is basically what we will need here. Okay, so from Gibbs Duhem equation, we get Na dxa, sorry, plus Nb dxb equal to 0, and if I divide it by n, both sides by n, so it will be xa dxa plus xb dxb equal to 0. So so you get this is xa, right? 1 minus xb is xa. Xa into dxa plus xb into dxb. So this term plus this term, according to this equation, is going to add up to 0. So this basically gives me that I'll give xb minus xa. Is that right? So basically I get del x by del xb at any location is xb minus xa, which basically says that at any location the slope of this would actually have intercepts on the two sides, which is xb and xa. So that is the thing. So it's a straight line relationship that you get, because this is, you can write it as xb by xa by 1. So when xb changes from 0 to 1, this changes from xb to xa. That is basically the relationship that you get. So del x by del xb is the slope of this curve. So if you go back to this diagram, so at this location, if I draw a tangent, which is the slope of this, but it will basically give me, this will be VB bar and this will be VA bar. Why? Because the slope here, del V by del XB, which is the slope here, will actually be equal to VB minus VA divided by the distance 1 between them. Right? So this is x is here, x equal to 0 and x equal to 1. So I can just draw a tangent at any location, and at that location the VB bar would be here and the VA bar would be here. Is that clear? So I can basically use for a binary mixture drawing a tangent. So measuring this is small v bar. Likewise, you can measure any x bar. Okay. So according to this expression, if I measure horrible vertical line, okay, so this is xb equal to 0 and xb equal to 1, and correspondingly xa equal to 1 and xa equal to 0, and I measure any property x bar, which is x by n for the mixture, and plot it here. The value of slope at any location will basically be equal to the two intercepts in difference. So this will give me xb bar and this will give me xa bar, which is clearly different from this is xa bar and this is xb bar. Okay, so these are the pure substance values, whereas this is as it exists in the mixture at this composition where you have drawn this composition xb, say xb star. So at xb star, this composition, if I draw a tangent, then the intercepts would actually be xa bar and xb bar respectively on the respective axis. So this is the a axis and this is the b axis, because here b is 0 and here a is 0, and accordingly I'll get this. So this is another way of measuring, but it's easy for binary mixtures. But when I have an n component system, this measurement becomes extremely painstaking, and we'll not have a two-dimensional graph here, but it will have a multi-dimensional hypersurface, and it will basically be calculating gradients at each locations, and you will basically need to take slices of that for each and take it like a binary mixture, saying that species I and the rest of the mixture. The rest of the mixture is treated like one substance and species I is treated as another substance, and you do the variation of this kind, and you do that for every other composition of the rest of the mixture. So that is how you measure partial molar properties. So you can understand that measurements are required, but they are really painstaking, and measurements are possible for volume, they are possible for temperature and pressure. The temperature and pressure being kept constant, the extensive properties that can be measured would be primarily volume, and with some difficulty and calorimetric methods which is indirect, you can actually get the value of changes in internal energy, and therefore that can be taken as measurable with some value of internal energy L0 as reference, and then from those you will need to evaluate the remaining properties. So that is how we determine the partial molar properties of the substances as they exist in a mixture. So for today's class, we'll stop at this point and come back in the next class to try and understand what the limitations of the measurement of these partial molar properties is, and what the difficulty with using the chemical potential is, and what is the alternative for that. So that is something that we'll see in the next class. We'll stop here for today. Thank you.